Welcome to Through the Lens, a series dedicated to reveal the people behind today's breakthrough in optics. For the first season, I'll be sitting down with fellow members of the optics department of FEMTO-ST Institute in Besançon. We'll talk about their research, what motivates them, and their personal journeys. Come along as we explore the human story driving photonics forward. Hello, Jacob.
Hello.
Welcome on the podcast. I'm so happy to receive you today and do an interview with you. I will start by introducing yourself a little bit, and then you tell me if there's anything you want to add about this. And then the interview is in three parts. We're going to first talk about the origin of your motivation for physics, then a bit more technical questions about what you're doing in your PhD, and finally it will be more about how to motivate students to go into physics.
Okay.
That sounds all right?
Sounds cool to me. Thanks for having me.
Oh, it's a pleasure. So you are a PhD student at FEMTO-ST,
Yep.
and your research is combining two topics: is 3D integrated photonics for OPTO electronic neuromorphic computing, right?
It's a bit of a mouthful, but yeah, that's it.
Yes. And if I understood correctly, you use two techniques that we will detail maybe a little bit later, that are two-photon polymerization and for machine learning assisted photonic design.
Exactly, yes.
Okay. And recently you had the opportunity to present your work in quite national and international conference, notably the PEPR Electronic, French Photonics Day, and the IRN Gold Mine.
Yes.
Right?
There we go. Yeah.
Is there anything that you would like to add in this description that I just made of you?
I think that's kind of accurate. That summarises the last 2 years of what I've been up to here at FEMTO, and except there's a lot of details which I'm sure we'll get into. And
yeah.
That, yeah.
Okay, cool. So let's go a little bit back in the past. I know that you grew up in Wales, right?
Yes.
And I would like to know about if there's a teacher or a book or a moment that sparked your interest for physics.
So, okay. So I get to talk about myself. Yeah. I suppose. So I suppose the first thing I guess to say about that is that I'm dyslexic. I was kind of diagnosed with dyslexia when I was 7. Before then I was always obsessed with like a book we had in my parents' house, which was an encyclopedia. Now I enjoyed reading about the topics from what I could understand, but I could never read or write, and it never came natural to me. And I guess from that point, like my uncle is a chemist, and he said to my mother at the time, like, you might struggle with reading, writing, but he'll become a scientist. And I guess that's kind of where it kind of started. I remember when I was like 10 years old, we did leaving primary school, we had to do an assembly, as we say in English, like a sort of performance for the rest of the class, and it's like, what do you want to be when you grow up? And for me, I was wearing my dad's shirts, a long white coat, and I was like, I'm going to be a scientist when I grow up. And I guess I've kind of carried on that passion ever since, really. I suppose physics, because I was always kind of drawn to the almost pretentious, I guess, when I look back at it now. When I was 16, like I had some really good physics teachers, and my science teachers in general motivated me. Yeah, so there was this quite popular TV show at the time called by a professor called Brian Cox, very well known in the UK, who would talk about the stars, and that kind of inspired me to kind of want to go further. Around this time as well, I was also getting more into mathematics. I kind of started to do it around 16 is when the mathematics started to get quite interesting at school, and I thought, well, hang on, it's actually, even though I think in school often it's portrayed as quite a rigid pursuit, there's actually a lot of imagination in that, and you kind of have to think about things in a different way, and that's kind of what I work best at in some ways, seeing things in a, yeah.
And do you think, you were talking about your dyslexia, do you think this slowed you down or actually motivate you to go further?
I would say it did both. On the one hand, I think it motivated me to go further because I think it makes you determined being dyslexic. You know, you see other people. Some people, when in class, other people would read so much easier than me. I'm quite a disorganised person still, and I find that very difficult, timekeeping. Mm-hmm. But the fact that I'm kind of used to these like challenges in everyday life, it kind of motivates me to go further and push through that. And okay. I kind of see it as I can see things that other people don't necessarily see and approach problems in different ways. Yeah. Like I use my hands a lot when I talk, or I'm kind of like, thinking in 3D and stuff like that.
Well, that helps, I think, to understand in a way. Like the non-verbal communication is so huge, especially with students. If you move, if you try to make gesture, I think it's actually helping for them to understand. But so in a way, it made your profile or your pedagogy stronger.
Yeah, thank you. Maybe I guess I was inspired by throughout my schooling, from childhood into university and masters, the professors, the lecturers that were when they showed their passion for the subject. Mm. I think physics and science in general sometimes does have a bit of a stereotype of being quite dry, but when you find people that are really passionate about it and take the time to explain things thoroughly and go through and nobody learns physics is counterintuitive. It's not something that comes naturally. I think for humans it takes time to learn, and I kind of enjoy that process of deconstructing. And when people show me that share that passion of deconstructing things, okay, it inspires me.
Yeah, and I have to say, when I look at your CV, I noticed that you study quite hard topics, especially back then during your bachelor in Nottingham. You were specialized in quantum Darwinism, quantum information, conceptual physics. I mean, this has not so much to do with what you are doing now. And maybe to more like a follow-up question. So, what attracted you to these fundamental areas of physics?
Like I said, maybe I was definitely young and arrogant in some ways. Quite simply put, I guess I was always inclined to initially at the beginning, and we're definitely inclined to the big questions. As a teen, reading popular science books or watching YouTubes as a teenager, you think, okay, quantum gravity, you're straight that this is going to you have these almost mythical stories now of the beginning of quantum mechanics. And I wouldn't say I was I always kind of I think I was drawn to two things. One, sort of fundamental questions, what is reality? What is this? Does it actually mean? Which that was one reason why I was drawn to them. I suppose the second one, I was always kind of drawn to such slightly weird topics. You mentioned quantum Darwinism there. I'll be honest, so this was a summer internship project, and I guess it was the title that intrigued me to start with. I was like, what does that even mean? How can... And then I kind of got into that, and I thought, the way... It was a completely different way of kind of thinking about physics, and it kind of... I don't know, it made you question why do we represent physics the way we do? From now, I might get a bit technical here, but it's not too technical. But we whenever you make physics is all about measurements. Whenever you make a measurement in physics, it's basically an event at time A and time B, and you measure the difference in that time. If you're trying to calculate speed or acceleration, it's always the different point in time. And as with quantum Darwinism, to me, and I'll be honest, I'm not going to claim to be an expert, and it was also a long time ago when I did this. It kind of tried to look at things from a different perspective, why should you measure things in terms of time and position? Why can't we measure momentum directly? Why is there always sort of an indirect measurement?
Okay, but you always need a reference, no? So what do you mean? How can you measure differently? Yeah, but I guess, what exactly? That's kind of the question. Why do you need a reference? Why can't you measure momentum directly? I'm interested. What did you find out? So I'm going to completely butcher this explanation, but effectively the idea was, okay, you had two particles that were quantumly entangled in a box. You fire photons into this box, and then you measure the deflection angle from that photon. And you basically you have detectors in different segments around the measuring different angles. So you can say, okay, well, the photon at this point is coming to this
spots. From there, you could infer the relative distance between the two particles, as we've shown. As in, so you kind of went from a purely quantum entangled system, not measuring the particles directly, but you could infer what the relative position between the two were.
Yeah, but relative position also means that you have a reference between them, no?
Well,
you always need something to rely on.
Well, you just know that there's two particles. Again, this is a purely yeah. You don't. So the reference is kind of the other particle as such. It's kind of itself, so to speak, because it's one system.
Okay, I understand.
And you do that by literally just kind of counting the number of times. You know, you measure a photon in this angle or this angle. I suppose the more interesting question is because, like I said, this is purely simulation. But each time you run the experiment, it relies on random numbers, so you will get actually a different answer each time. Which I think is actually more the interesting question. Why should it change each time?
Yeah. So now you have shifted completely. You moved to France. You did your master in Besançon.
Yeah.
And you transitioned to neuromorphic photonics, right?
Yes.
So, what triggered that pivot?
What triggered that? I wanted to do something a bit more hands-on, should we say? So the masters, there were two motivations for this. One, I was thinking of my own career prospects, like, you know, doing a degree in mathematical physics. Okay, yes, it's multi-use, but if I actually want a job, I want to do something a bit more practical. Hence why I started looking for sort of physics or computer science-based masters. The second one, then I kind of, during COVID, I guess, it kind of dawned on me, like, you know, I've spent most of my academic life, you know, my education, I was kind of going for these like really, you know, big fundamentals of what is the universe questions, and maybe it was the fact that I'd lost all my freedom and I was stuck in a flat, not being able to go out, but it kind of told me, like, actually, I don't know how a computer really works. And you realize there's a lot of physics and a lot of science on so many different levels that goes into this. Yeah. So I found the masters in computational physics here in Besançon. We then had a lecture on laser physics, and then I had this other sort of similar epiphany. It was like, hang on a minute, but one of the most obvious physics phenomena that you see every day, is light. Mm-hmm. And then I met Daniel. I found out, so there's people trying to combine this sort of like idea of information and computation using light rather than using electrons. And I was like, oh, wow, this sounds very like interdisciplinary, very sort of unconventional ways of thinking, but it's also still very hands-on and practical. And it kind of made me reconnect to the sort of, you know, at its heart, like what physics really is. It's a science. It's not just some sort of philosophical, mathematical pursuits where you stood in front of a blackboard, which I think, you know, I kind of fell for growing up, and I realised it was not me. I needed
experimentation.
Yeah.
Okay.
And so it was kind of a gradual transition. First from, you know, like I said, maths to then sort of more. I thought, okay, computer science. I thought, okay, that's a bit more practical, simulation physics. And then I was like, actually, no, I actually want to be seeing things in real life and know how you actually measure these things. Yeah.
Can you describe your PhD topic in a few words for, let's say, level master student?
A master student level, okay. So here goes, no pressure. So the big global picture, I guess, is currently with the motivation, I guess, is the electronic computing, so digital computing, how our phones work, how everything in this room basically works, relies on digital computing. You don't need me to say this, I think everyone's aware that the demand for this is kind of increasing more and more. Most computing is based on von Neumann architectures, and for various technical reasons we're reaching limits, and it's becoming more and more challenging to improve on this and to keep up with demand. So my topic is kind of to the global idea that the research we do here is, can we replace certain parts of a computer with optics, with light, rather than using electronics. So what I do, I try to I fabricate optical interconnects, so these are effectively mini fiber optic cables. I try to arrange them into some form of circuit for use for computing applications. So that could be sort of literally just replacing electrical wires, so the transfer of information now, rather than it's done electronically, it's done optically. But also I kind of try to do sort of computation with these circuits as well. So most notably I try to arrange these mini fiber optic cables in a way that you can do some sort of maths operation on them.
Yeah.
Most notably matrix vector multiplication.
So can you explain why, in this case, optical signal would be better than electronic ones?
Why would it be better?
Yeah. Or why do you want to replace them?
So the big, I suppose, I would say two reasons why we could say we want to replace them. One, it's the energy consumption. Light uses considerably less, and the propagation of light is considerably more energetically efficient than using that of electrons or electronics. There's also sort of unique properties of light which you can kind of take advantage of, which you cannot do using electrons. Specifically with my project, we don't want to kind of replace electronics completely. The idea would be kind of how can we integrate optics with electronics and kind of use the best of both worlds.
Mm-hmm. Okay, and to construct these mini fibers, as you said, I like the term actually, you use what is called two-photon polymerization, right?
Yes.
Can you explain a little bit what it is and what's the process?
Okay, so effectively the way we build these sort of, we'll stick with the term mini fiber optic cables, we use effectively a 3D printing technique, which takes advantage of, like you said, a process called two-photon polymerization. So we use a commercial machine in the clean room here in FEMTO. You take a liquid resin, you then, you put it in the machine, you then you direct a femtosecond laser to the spot in the resin which you want to harden, polymerize, turn into a solid. And then so what we do is we design a file of what the interconnect will look like, and what my 3D design wants to look like. And then we build that up voxel by voxel via this two-photon polymerization process. And the way this works is, for those, a femtosecond laser is a very high-powered laser. You would not want to get it in your eye, to say the least. What it does, it's kind of the polymers inside the resin can absorb 2 photons at once in a very precise location. That allows for a free bond for then these polymers to join with other polymers. And slowly you build up chains of these, which are now no longer liquid, but are actually solid.
Okay.
And you kind of do this, yes, repeatedly, for each voxel by voxel, so each block by block.
And can you explain why this specific technique of 2PP is suited for 3D photonic circuits instead of the 2D one?
Are there advantages to 3D or 2D? Now, another issue, if you want to compete, one of the big issues with electronics at the moment is the fact that we are literally running out of space on our microchips. A fundamental point of computation is you need lots of inputs and lots of outputs. In 2D, this scales quadratically, the physical size of the area. But that's not the case in 3D. In 3D, and if you think about this long enough and look at pictures, you can see straight away this only scales linearly. So effectively, you can have a higher density of inputs and outputs with a higher density of connections between those in 3D than in 2D. So that's the motivation why we do this in 3D.
Yeah, space
rather than in 2 dimensions, like maybe what you'd see in conventional electronics or in silicon photonics. The reason why you might ask the question, well, why can't we do this in 3D? Well, with electronics, this is another advantage of optics has, is literally in electronics. Like I said earlier on, the heat is dissipated, it loses a lot of energy. So if you did 3D electronics, is very difficult to do. It's starting to happen, but still, what's the problem they have there? It literally melts because of the heat transfer. In optics, we don't have this same problem because the dissipation of there is. Okay, technically there is some dissipation of heat, but for intents and purposes, no, there isn't in photonics or optics.
Yeah, and energy-wise, it's, I mean, can you not like just cool down the system in order to have electronics in 3D?
I know people try to do this. I'm not far from there, but like I think the problem is because one thing we do with these fiber optic circuits I want to design, we want lots of interconnects. We want lots going on inside of the, like say, this cube of. In electronics, you can't really cool the inside. With photonics, we don't have the same problem. You can cross them over. You can have a higher density without it being an issue.
Okay, and. Can you tell me about, because right now we talked about limitation of electronics. I want to know about the limitations about the 2PP technique. I had some feelings about, for example, optical loss might be one, or the voxel. You talked about the voxel. Probably the voxel anisotropy can be also one. I'm not sure. Like, can you develop on this?
So let's start with the obvious. The people have done, they have created a lot of optics using these techniques. But like you said, one of the limiting factors, there are still losses which kind of need to be accounted for. It's still kind of a bit of a random process when you do the 3D printing. It depends on many different factors, like the temperature of the room, how the laser is calibrated at the time.
And I mean, just the fact that you have such a small scale, like how long are we talking for your waveguide?
Yeah, so my waveguides I built are quite big. Mine are about 200 microns long.
200 microns. It's not big.
Well, it's not big, but you can see it with your eye. Just about.
So at that scale, I mean, everything is kind of redistributed, I would say. Like when we talk about voxel, when you talk about temperature, everything is different.
Yes.
So sensitive. That's what I. Yeah.
You know, exactly. Like one of the biggest challenges, not necessarily the waveguides themselves. It's the you have to think of the mechanics. You have to put the scaffold in. You must make sure that to kind of hold the waveguides up, but also you must make sure that the support structures do not affect the optical properties of the waveguides as well. Okay. So it can be again for me, like I kind of love that aspect in some ways, because my background has been very theoretical in a perfect world. Now I'm kind of going in the more engineering side of things, which is interesting. Use it a different part of my brain, which I'm not used to. Well, I'm getting used to now.
And how do you validate those waveguides? What are you measuring actually to say, okay, this is good, I can use it to replace some part of electronics for a future network?
So it's compared to a lot of the experiments here, mine is kind of simple. Effectively, we couple the light at the input and we measure the output. And we kind of look at, specifically with my project, we're not too interested in whether it's single or multi-mode for what we're trying to do. But we are interested, like for example, if you have a waveguide that splits into 4, you want to make sure that the distribution between the 4 outputs is equal. But you want to again make sure that the losses aren't too high. If you want to have a circuit, if you want to kind of build, if you want to completely replace all the wiring in an electronic chip, for example, photonically, well, you need to make sure that there's still light at the output when you get there. So one is the optical characterization. We also then use the SEM, scanning electron microscope, to look at the physical structure of how sound they are. You also, because these things need to be robust, right? You can't just have something that's going to fall apart after 2 weeks if you want it to actually be a viable option for anything useful. So we look at that. The first time when I was playing with the experiments, I did actually drop one of my samples, and it survived. So I take that as a sign that they're fairly strong and sturdy for now.
Best test ever. Yeah. I mean, when you say I measure the input, measure the output, etc., it's put so simply. I don't think it's how can I say this? It's so difficult to imagine the amount of technology and the amount of research found and innovation that is behind this. Like I actually love this. It's like you succeed to simplify what you're doing, but it's to simplify the explanation of what you're doing. But it's an enormous work that is behind. For now, I would say a few more generation of PhD students than yours, right?
Yeah.
Yeah, yeah. Just to make sure that it is in context. So
it's like this. These techniques did not exist, 10 years ago. I think it was like 2005 when two-photon polymerization became a thing. It's only in the last 2 years that's been kind of commercialized to the point that research labs can start actually doing more.
Yeah.
It's kind of crazy. It's crazy.
Yeah,
it is crazy.
It's really crazy. I think so too. We navigate quite a lot of concepts. There's one that we touched a little bit with all this data center growing everywhere, but it's about scalability. Maybe can you tell me more in your research how scalability looks like? I guess there's like some fabrication complexity that we are not really aware of, and or nodes and density like that. Do you have can you mention what is scalability for you?
Okay, so scalability. So okay, like you touched on the two aspects. I guess you've got the fabrication constraints. If you want this to actually scale to a level that is able to be commercial, you need to be able to produce many of these 3D printed interconnects very fast at a scale comparable, or at least a useful time scale compared to electronics. Is that possible for the moment? Well, it is still very much the beginning of that. Like you've seen in the last year, you have big chip manufacturers, notably Nvidia is the classic one, where they've started they want to use optical interconnects on their chips. You also have a lot of startups at the moment that are kind of coming up all around, Europe and North America, all over the place. So I think people believe there is definitely a potential for that to scale up to a point that it can be fabricated in a viable scale. Whether, I guess this is the thing, electronics is so dominant, is it going to be able to keep up? Like it's going to make a very strong case to do that. Yeah. But I think it's getting there. I think there are people actively researching, still looking at this 3D printing technology. How can the two-photon polymerization, how can you do this in more interesting ways or different ways? How can you speed up the process? Like there's work in the team that have done that as well to try to speed up the process. But yeah, I would say that for the moment, like in terms of one of the big issues, is how do we print these faster and more efficiently? So the other one, more like a fundamental issue, is how, like you said, about the size of the circuits we can produce. They are limiting factors with that. People have printed waveguides that are a millimeter in length with this technology. But to what extent, how far you can actually push this, it's still open debates.
Yeah, and I want to be a little bit controversial right now, but don't take it personally. I'm saying it's not because there's a lot of money that it will obviously succeed. Like for me, it's not because there's a startup growing everywhere. I mean, of course, it means that people have a vision and they want to, they believe in it. But there was example in the past that money was invested, millions and millions, in some, and it crashed for whatever reason, technological or lacking whatever hand. But so I agree with you that it's still up to debate if we can achieve this. I mean, obviously, if you work in this, is that you probably believe that it could help at some point, right? Or
I think that there'll be obvious. There will be some form of application from this. Whether, like you said, you just need to look at the last 30 years. You had the dot-com bubble at the beginning. Everywhere, like this seems to. We could say we were maybe in an AI bubble at the moment. Definitely are. But anyway, that doesn't, you know, I think that's kind of just the history of technology over the last 200 years in some ways. You know, some people try things, sometimes it works out, sometimes it doesn't work out. I guess at the time you don't know until 50 years in the future what the actual consequences of it are. I'd say one thing, like I think, you know, you mention about, like, there's something in the next 50 years it's going to have to change. Like I said, we are reaching fundamental limits with the current technology. Okay, maybe somebody will come around tomorrow and kind of solve all that problem. That doesn't really address the climate change and the issues that are caused from that. Yeah. So I guess it's worth pursuing every pursuit is what I would say. And at the very least, I think it's academically quite interesting to show that this, you know, to what extent can you use the properties of light to kind of encode information. I think that's actually something I find most interesting. Like maybe this is slightly arrogant, but like, can you make a photonic brain, for example? I think that's actually kind of an interesting pursuit to pursue purely academically, and I think
definitely. Yeah. I think we talked about your PhD. I want to move to the last part now. That is a little bit, actually, you made a perfect transition, going what is motivating for you. So what advice would you give to students who find physics like intimidating?
Intimidating?
Yeah.
I would say everyone finds it intimidating to some extent. So the first thing, it's just like, you know, I think we've all been there before at some point, and like you be it reading a textbook or sat in a class and like, I have no idea what's going on. That doesn't really, you shouldn't reflect on your own ability. That's just because, you know, maybe the way it's explained isn't very good or not suited to your style. Maybe just some things that just take time and hard to, you know, just be patient and gentle with yourself, I guess. If you have a passion for it, don't let the intimidation get in the way, I suppose.
Yeah.
Like, yeah, if you have the curiosity and if you find it fun and enjoyable, then you kind of push through the intimidated times.
True. Mm-hmm. And you also have, I mean, you were a student, but you also have some experience as a teacher, right?
Yes.
Can you tell me what you've learned, what you've experienced in this matter?
Teaching, I would definitely recommend if you do a PhD. Teaching is definitely something that I would recommend. I was teaching a class on Introduction to Python, a programming class. Now I've been coding in Python for I don't know how long, and I've realised quite how second nature it was for me. And then I realised pretty quickly, for a lot of people, it's for new people, it's completely new. It's very intimidating. Going back to that, so it really made me think about, like, I had to kind of think about how I approached programming and like what I needed at that time. Like I think empathy was really a big part of this. Like, no, I have to remember. Okay, well, back in the day, I didn't know what print meant. I didn't know what a terminal was. I didn't know how to install Python, and it was a good experience to how to think through your thoughts and how to present it in a way that other people understand.
Yeah.
So it was a challenge which I kind of enjoyed, and also I hope I helped them a bit at the very least.
Well, hopefully. I mean, I'm sure they would say so.
Yeah.
You were teaching in master, right?
Yeah, so I was teaching first year master's students.
How did you handle that the age gap between where you and them were so close, and still have like a figure of professor to them? Like, how did you do this?
At first, it was quite. It was kind of bizarre, especially people, some of them did call me professor, and I was like, "What? Excuse me." It was definitely a bit of imposter syndrome there. But I think it helped in some ways. Like it was still fresh in my head what it was like being in that position. So I could kind of, I wouldn't say I necessarily could anticipate the issues that they could have, but I definitely was aware that I knew there was going to be issues. So I was kind of prepared for that, and I was kind of prepared to try to like I go slow and kind of like use, in some ways, like one thing I did a lot of, like now with the internet, I knew like where to find resources. I was like, okay, well, I might, if you find any issues, you should look on this website or look on YouTube, or don't be scared to look at multiple different sources and work your way through this and kind of work it out. So actually the biggest shock, if you want me to keep talking about this, one of the biggest shocks in age was, obviously when I did my Masters, ChatGPT didn't exist. Now that it does exist, that was one thing I didn't quite anticipate.
It's a pretty big rupture, no?
It is, like, I use AI for coding all the time, but the thing that kind of done me is like, oh, well, these people, some of them did not know how to code in the first place. At least I can read the code and tell you if it's wrong. Well, sometimes I can anyway. But then I had to really emphasize to them, like, no, actually try to understand what's going on. I know you're going to use it, but be conscious that it might give you the wrong answer at times.
Yeah.
So I did feel quite old in that situation, actually, when I realized that.
Yeah, AI is reshuffling the cards when it comes to teaching completely. I think it will develop in the next years new tools to solve this, because you need to do it by yourself sometimes. Yeah,
that's for like the sciences. Who knows?
Some general questions to finish.
Okay.
A few. Where do you see 3D photonics computing in the next 5 to 10 years?
Where do I see I think there will definitely be some applications in somewhere. Whether I think like I've mentioned in video already. I think in on-chip connections is almost certainly the way forward.
I hope so.
For me at least. Yeah. I think that we might. I think the field is probably going to get bigger. I think as more people start to realise, like, how it's still a relatively new field, still quite untouched. I think the big one is going to be very much pushed towards the integration of these things and how we do actually miniaturise them. Like we've done, the first optical computing experiments, the neuromorphic was done in the 80s, but it was on a massive optics table. Now this is becoming more and more compact. So I see that being an increasing field.
Will it ever be competitive to digital ones?
I think there should be a synergy between the two. I don't think it's ever going to. It's never going to completely replace electronics. But I think it could be. There could be a time where it's more, this opto-electronic. We kind of use both at the same time.
Yep. One last question for you, totally unrelated. So I've learned that you do like climbing in narrow caves. Can you tell me what fascinates you about this?
Cave-in speleology. Yeah. It gets you out into nature. You go into you go into a cave. You don't really you go to explore. It's kind of using your body, your mind all at the same time. You're cold and wet. It's kind of, but you kind of have the motivation because I want to get out of this squeeze. I don't want to be stuck here for the rest of my life. And it's if I sound again a bit pretentious, we've climbed basically every mountain of the planet. You're never going to go to the bottom of the ocean because it's too much pressure. But there's still caves even within an hour of Besançon, which no human being has ever gone to before. And I kind of like that sort of exploration aspect to it. And you see things that other people don't, they can be quite pretty sometimes. Yeah,
I see some parallel with your research life. Okay. Jacob, thank you very much for this interview. I enjoyed thoroughly, and thank you for taking the time to answer all my questions. And it was a pleasure to have you on the podcast.
Thank you for the invite. Cheers.
Cheers.